As part of the research we are doing during our RET program, Ken and I must learn how to use several pieces of equipment. As mentioned in our blogs, these pieces of equipment are called Iris-Maldi TOF, or interferometric reflectance imaging sensor, and matrix-assisted laser desorption ionization with time-of-flight measurement. Together, these technologies measure and identify the target antigen protein that will be bound to the antibody probe. However, there are several preparatory steps that must be taken before we can use either piece of equipment. We must first pattern the chip that will be used throughout the experiment. This process begins with a silicon chip that is covered with a layer of oxide. We then add a layer of photoresist to the chip, which will protect the oxide that lies beneath. However, we need to remove the oxide on some parts of the silicon chip. To do this, we use a photomask to expose and develop specific locales of the photoresist as is seen in step 3. As we still need to remove the newly exposed layer of oxide, we use buffered oxide etch solution to etch away the exposed oxide. We now have a silicon chip with a patterned layer of oxide. The next series of steps that need to be completed are those followed in polymer patterning. The first thing we do is take the patterned oxide chip we just made and add a layer of HMDS. This substance is highly hydrophobic and repels water and water-based solutions where we do not want them to be. On top of this, we add another layer of photoresist, which we then pattern with exposure through a photomask. We now remove the exposed HMDS with a process called plasma etching. Thus far, we have a silicon chip with patterned layers of our photoresist, HMDS, and oxide. Now we take the chip and incubate the entire chip in polymer solution. This polymer is going to act as the anchor that helps bind our probe, the antibody, to adhere to the chip. Once incubation is complete, we remove all remaining photoresist as well as extra polymer to create the final chip that can be seen here. This picture makes it clear that the majority of the chip is a silicon region with a hydrophobic surface due to the HMDS layer. The remaining area consists of spots of oxide with a center spot of polymer. These spots are where we will attach our probe antibody. Using a micropipette, we place a small amount of probe antibody on each spot. Once each spot was covered with antibody, the chip is placed in a humidity chamber overnight to keep the antibody moist and active. The next day, we clean the chip with a series of washes that includes a detergent to clean any antibody that may have bound to the chip outside of the polymer spots. The chip is then incubated in the target antigen solution for 2 hours and cleaned again with a series of washes. Throughout this process, we measured the chip with Iris after adding layers of polymer, antibody, and finally the antigen. What we are looking for in the final measurement is a height difference of enough significance between the antigen and antibody layer, which would indicate that binding did occur between the antigen and antibody.
The iris can measure heights as small as 1 nanometer using nothing but light. Our chip is placed on the stage of the iris using an LED light source of 4 different wavelengths. A beam splitter redirects the light down onto the stage. Some of the light will reflect off the topmost layer of the chip, the layer of antigen. The remaining light will pass through the other layers on the chip to the silicon base and is reflected back from this surface. The 2 light rays pass back through the beam splitter and travel into the camera. The Iris software analyzes the interference pattern from these 2 superimposed light rays, which reach the camera. As you can see in this diagram, adding biomass, such as the layers of antigen and antibody, can change the optical path length that a particular light ray follows. This change in path length between the 2 light rays registers as a phase shift between the different light rays. Since this shift is proportional to the difference in path length, the measured phase change in the combined ray provides us with a direct measurement of the thickness of the biomass. After we have run the chips in Iris and have observed a significant difference in height measurements, we bring the chip over to the medical campus. This is where Maldi is located. Before we can analyze the chip in Maldi, we must first add a layer of matrix to assist the laser in blowing up the bound antigen substance. Again, using a micropipette, we add 1 microliter of matrix to each spot. Once this has dried, the chip is ready to be run in Maldi. The structure of Maldi is pictured here. The chip is placed on a tray and inserted into an evacuated chamber located here. Using the software, we focus the laser light onto a particular spot on the chip, which is to be analyzed. We then shoot the laser in a series of rapid pulses. This energy is absorbed by the matrix. The matrix transmits its energy to the antigen target sample. These pieces are ionized to their smallest possible structure and are forced down the length of the vacuum tube to reach a detector. This detector measures and transmits the time of flight to the computer. Using the time it took for the pieces to reach the detector and the concept of energy conservation, the mass of each piece can be calculated. A graph, which will then be produced, that shows the relationship between the mass per charge ratio of the pieces and the intensity of the energy of each relevant mass. Once we know this, we can identify the protein that was in the sample.